In this video, we will explore the step response of an RL circuit. An RL circuit demonstrates the step response when an independent voltage source is abruptly connected to it. Let's analyze this response with the help of a following example. We have an inductor with an inductance L connected to the voltage source Vs through a resistor R along with an ideal switch. The switch is initially open, and at time t is equal to 0, the switch is closed, changing the circuit from an open state to a closed one. We assume that the energy stored in the inductor at the time the switch is closed is given as a non-zero initial current I0. Our goal is to find the voltage across the inductor and the current through the circuit after the switch is closed. At time t is equal to 0, the switch closes, and we apply the Kirchhoff's voltage law. Rearranging the equation, we get, from this equation, if we take the I term to the left side, we will get. Now we will perform integration from time t is equal to 0 to the time t. Now to find it, we integrate both sides from time t is equal to 0 to t. Given that the initial current is I0, we will get. We know from the standard integral tables that integral of 1 over x minus a is given by ln modulus of x minus a plus c. Thus, the above integral becomes. Taking the inverse of logarithms and solving for it, we get. If the initial current is 0, that means I0 is equal to 0, this expression simplifies to. This expression can be explained as follows. At time t is equal to 0, the current through the circuit is 0 because the inductor resists a sudden change in its current. As the time progresses, the current gradually increases, approaching a steady state value of Vs over R as time approaches infinity. The current increases exponentially as shown in the graph. The behavior of an inductor current can be explained by the principles of inductance. An inductor opposes changes in the current by generating a magnetic field. When the switch is closed, the voltage source Vs tries to push the current through the inductor. But the inductor resists. Initially, the current is 0, but as the time passes, the opposing voltage decreases due to the collapsing magnetic field, allowing the current to rise gradually until it reaches a steady state. At steady state, the voltage across the inductor becomes 0, and the current is determined entirely by the resistor R following Ohm's law of I is equal to Vs over R. The term R over L defines the rate at which the current or voltage approaches its final value. The inverse of this term, which is equal to L over R, is called the time constant. After one time constant, the current reaches about 63% of its final value, and after 5 time constants, the current has essentially reached its steady state value. From the expression of the current, the inductor voltage can also be derived. We know that the inductor voltage is given by VL is equal to L di by dt. Taking the derivative of current expression with respect to time and simplifying, we get. If the initial current is 0, the inductor voltage jumps to Vs at t is equal to 0 and decays to 0 as the time progresses. A real-life example of the step response of an RL circuit can be seen in the behavior of an electric doorbell with an electromagnet or in inductive loads such as motors. When the doorbell button is pressed, a switch closes and the voltage is applied to an RL circuit that consists of electromagnets, inductance and resistance. The current starts at 0 and rises gradually, following the step response of the RL circuit. Eventually, the current reaches a steady state, allowing the doorbell to ring. This concludes our discussion on the step response of an RL circuit. In our next video, we will explore the step response of RC circuits. Thank you for watching and stay tuned.